Okay, let's get started then. So photons are the topic, and as I said, it is the longest of the topics, so we may need a break in the middle. Which would be broken into two videos on here. Okay, so we're learning about Einstein's photoelectric effect, and how light is sort of not a wave. It's also sort of not a particle, but we'll get there. Okay, so at the end of the 19th century, they were like, yeah, we've got this. Done. Easy. We've worked out what light is. And everyone was like, cool. Alright, cool. What else would we do? I'll sit around and do nothing. There was a period where they didn't really do much in physics because they thought they'd worked it all out. As far as optics and light is concerned, this fellow named Heinrich Hertz, which you may have heard his name Hertz from the rent-a-car company, no, from Hertz as in frequency, and he discovered that if he had two posts, there's a voltage between them. Under certain conditions in the dark, for example, there wouldn't be a current between them, so there'd be no spark between them. But if you put a light onto them, it'd spark across. To you, that might seem like, oh, cool, that's not much of a thing. But to the people who thought that light was a wave, there's no way that a wave can cause that to happen. So the light that he was using was ultraviolet light, and the phenomenon that he was observing is known as the photoelectric effect, which we will discuss in very great depth later on. Cool, so in 1900, Max Planck's constant, which we have not looked at yet, so Planck's constant is a thing we'll be doing soon. Was able to derive an equation that described the radiation curves that are emitted from oscillating atoms, so that's atoms moving backwards and forth. But for this to happen, he had to assume that the radiation from these atoms was not emitted continuously, but in multiples of a minimum quantity.
So lots of little things to come up.
Yeah. What that means is, so it's moving like this, do a little bit of movement, you would expect a little bit of signal. Almost none signal coming out. But what he discovered is there were, so you could move a tiny, tiny little bit and have nothing come out. And then it goes up, goes up, it goes up. So it's not a continuous spectrum. Which was odd. So he, had to assume that in order for his theory to work. So this idea of little packets of energy went against light being a wave-like form in nature. So in what is known as his extraordinary year, his Annus Mirabilis, Einstein released a whole lot of information, a whole lot of studies that he finished in 1 year. In fact, he described the photoelectric effect, E equals mc squared, Brownian motion, and relativity in 1 year. So there's more output than you'd probably do in your entire life he did in 1 year. So that's pretty interesting, pretty cool. Einstein would explain this. Sorry, that's all right. in that year. So he'd explain why this has happened. So let's have a look at this. So consider the interference pattern that you'd normally get from Young's double slit experiment. What do you normally see? You have double slit and you get center, pattern, darkness. Light, darkness, light, darkness. Remember that one? That's what you normally get. As the light source gets brighter, the image gets brighter. And as it dulls, the image becomes fainter. However, at extremely low levels of light, basically when you set up the apparatus in a dark room where there's only like one photon come through a second or whatever, you get something like this. Now, can you see what's up there, or can you see it in your notes?
Yeah.
There are dots, just random dots everywhere. And as you leave it for longer, you get random dots everywhere, and eventually it starts to form that image of bright, dark, bright, dark, bright, dark. That does not look like a wave pattern, does it? Does not look like waves interfering. In fact, because we know that there are very few waves or whatever coming through, very few light bits coming through at once, it can't be interfering with anything else. So instead it has to be interfering with itself. And hence you get that. So you get those dots at random spots. So the plate appears to have just random scattered points of light. And if you leave it, it increases, so you get closer to this, what we would normally get. So we normally don't observe that only because we put so much light through it. In fact, we put heaps of light through it when we use the laser. But if we could just put one little pulse through, we'd get dots every time there was a pulse. And these little bundles that we observed there, which we now sort of know exist, are photons. So that's where photons meaning small bits of light. So Planck determined that a subatomic oscillator, so that is something that is tiny, that is moving backwards and forwards, like an electron, or a proton, or a neutron. It's moving backwards and forwards, not a neutron. Proton or an electron. It's moving backwards and forwards really, really fast. The energy that it has, that it emits, the photon that it emits, is E equals hf, where F is the frequency and H is Planck's constant, named it after himself. I don't think he did. Someone else probably named it after him. But Planck's constant, which is this. That Planck's constant, do you think you should remember it? Why? Because it's on the cheat sheet. Good, well done. You're going to be using that a lot in the second half of this, like the semester. When a very high energy photon is emitted, like a gamma ray, the energy per atom is still very small. And the energy can also be found with this. So the actual energy there is quite small per photon. But if you've got, say, a laser and you've got billions of photons in one beam at one point, you've got lots of energy. Okay, so we're still at the postulating, coming up with this idea of photons thing. And if they are photons, they must interact with matter in the same way that normal particles do. So what happens when a particle, maybe a tennis ball, hits a wall. It bounces off it. You don't need to be as complicated as saying it bounces back off of it. Do you expect light to bounce back off a wall? Sort of.
Some of
Depends on the surface. And some of it, that's right. But some of it goes through it or into it. That's what we normally say. So, and the important thing is that we conserve momentum. Law of conservation of momentum being really, really important in physics. Okay, so in 1923, Compton discovered that when a photon of light interacts with electrons, the particle would move in such a way that the total momentum of a system would be conserved. I have no idea how we would do that, because can you imagine just staring at an atom, being like, aha, it moved, I'm right. But that's what he discovered. So that's what we'd expect. So I throw a tennis ball at you, Connor, and it bounces back off of you, back towards me. You get some of the energy, you get some of the momentum, that is, and the ball gets some of the momentum, based on how much momentum was in the system to begin with. That is what he showed happened with light. Beforehand, they didn't think that would happen.
So there's no light.
No, well, yes, there is wasted energy.
But there's still
So-
that's
Yeah, so the total energy of the system, the total momentum of the system as well, the change is zero. There's no change in momentum. There's no change of energy. It's just some of it turns into heat and sound and light, things that we can't use. Okay, one problem that we have with finding momentum to a photon is, what's our equation for momentum? Momentum's P, mv. P equals mv. P, momentum, equals m, mass, times by velocity. What does light not have? It does not have mass. So that's a bit of an issue. So we can't really use that equation to assign momentum to something, can we? Then we get Einstein's work, which is really helpful, and from Einstein's work we know that E equals mc squared and that mass and energy are convertible. Light has no mass, but what does it have? Lots of energy. Energy and mass are equivalent. So we can use that to help us work out the momentum of the system. Compton also discovered that photons are constantly moving and that they have no rest mass. They instead have what's called a relativistic mass. So they don't have mass like this book has mass, but they have mass from their motion, from their movement. And they are constantly moving. So, yeah. So the energy of a photon from before is E equals hf. But we also know that E equals mc squared. So we can equate the two. We can go mc squared equals hf. And we can say that, well, F is equal to C over lambda. Have I lost anyone yet? Just that F equals C over lambda part? Yeah, that's it's what we call the wave equation, which we've done with these guys. It's just a thing. It's basically the same as V equals S over T. Mostly. Okay, so we can rearrange that and we get M equals H over lambda C. So M is mass, the relativistic mass. H is Planck's constant. Lambda is the wavelength or frequency? Wavelength, good. And C is the speed of light. which is constant. So there are two constants on that side of the equation. Lambda, it's h and c. So it is only dependent on the wavelength. What happens if you have a really small wavelength? To the mass. Well, it would be less mass and then less energy. That's right. Really big wavelength, more mass. Huge wavelength, well, like, yeah, small mass. So that's the relativistic mass for photons. If this is substituted into our P equals mv, then we end up with P equals h lambda c. C is the speed that they're traveling at. The two C's cancel, so we get P equals h lambda over lambda. The momentum is equal to the Planck's constant divided by the wavelength. They're inversely proportional. So the larger the wavelength, the smaller momentum. Okay, so previously we've seen that there's a spectrum of electromagnetic waves. The energy of a photon is directly proportional to the frequency. Therefore, cosmic rays, which are the most energetic, they carry the most energy. They are the shortest wavelength, they carry the most energy. Radio waves are the longest wavelength, they carry the least amount of energy. We can visualize a photon sort of like this. So it's a bundle with a wave inside it. And we've got these bundles carry several hundred wavelengths inside of them. So that's a bit confusing. So each photon doesn't quite relate to one wavelength. A little bit weird because I'll jump the gun here. Light is not a particle, it is not a wave, it is not those things. It is a superposition of both. It is sort of bits of both, and then bits of stuff that we can't even imagine. It's weird, basically. Okay, on to the photoelectric effect then. So when you've got an electromagnetic wave with a significantly high frequency that's incident on matter, we normally talk about metal surfaces when we're doing this, but it does apply to most types of matter. The photon will be absorbed and an electron is emitted. That's what Hertz saw. So he had a light set up, photons were going in, that was making electrons more likely to flow across the gap between the two poles that he had. And this is known as the photoelectric effect. Some common applications of the photoelectric effect are photovoltaic cells. Who has solar panels at home on their roof? Anyone? Couple? Cool. What happens there is the cell is struck by light, it emits an electron, the electron is then driven by voltage and it produces a current, to put it very simply. And also those security devices, when you walk into the store and your leg goes through the beam and it goes doo-doo, like to say you've entered the store. That's an application of it. There are many other applications of it as well, but they're just two simple ones. The textbook is so old that it doesn't talk about solar panels. I don't know if it's because they didn't exist when the textbook was written or what, so that extra little bit there about solar panels I've put in. That won't be a problem for you guys next year. So a photoelectric cell has a semi-cylindrical metal cathode and then a wire running down the middle of it. So it's got this big bent bit like that. You see that? And down the middle just down the middle is one wire. And it's an evacuated chamber. There's no air in there. It's a vacuum inside. The two electrodes are connected by potential difference in such a way that the semi-cylindrical bit is negative with respect to the wire. When the tube doesn't have any light on it, no electrons flow, so there's no current. When the light is on it, electrons are going to start flaking off that back part. Now that back part is negative relative to the wire, so where are the electrons going to go? Towards the wire. When they get to the wire, they've completed a circuit. Well, not quite, but they've almost completed a circuit. They make current. So you get current flowing, and hence you can get power from this sort of thing. Which is cool. When we have this going on, when we have the light illuminating on the cell, we can find experimentally that the electrons are emitted with a range of kinetic energy ranging from 0 up to an absolute maximum. So from 0 to a maximum. Not continuous though. The maximum kinetic energy of the electrons is dependent on the frequency of the radiation and the surface that the electrons are being emitted on. So certain metals perform this effect better than others. So the metal on the chair might be worse at it than the metal on the posts. They may also be the exact same metal, they might just be steel. The metal on my watch might be better at it than the steel is. It's hard to tell. For you two, if this is not making a huge amount of sense, that's okay. Just wanted you to come and sort of take it in, because we've seen it a few times and it makes more sense every time. We don't do this in year 11. So the maximum kinetic energy the electrons will have can be determined using the following experimental arrangement, which we are going to do as our next practical. So I have a piece of equipment out the back. It's called the photoelectric effect device, and we're going to do this practical. So we'll have it all connected up with a source of variable voltage, and we'll have the connections in the reverse, which means that the back part will be positive and the wire will be negative. We'll have light from a particular frequency come through, and it's going to radiate the cell, and we're going to have a potential difference of 0, and you'll have current flowing. As the voltage slowly increases, the current will decrease. So we're going to get to a point eventually where the electrons can't reach the back of the cell. When that's the case, that's the maximum energy you've got there, and we can do that. So if we do that with red light, it's going to be much lower maximum kinetic energy than if we do it with purple light or infrared, and not infrared, ultraviolet, or X-rays, or so on and so forth. We can't use X-rays though, we don't have an X-ray machine. Okay, and the energy required to cross the gap is E equals little e, so what's that little e? Charge of a charge of an electron, and delta V would be the voltage that you've got. So we can work out the energy that each electron has by just timesing the charge of an electron by the voltage that we have. When the current's at 0 amps, most of the energetic electrons are stopped from entering the wire, and we call this the stopping voltage. Therefore, the maximum kinetic energy, K max, is equal to E times V, that maximum stopping voltage. All of which we can determine with the experiment. As I said, we'll probably do the experiment next week, but it might be the week after. See how we go. Okay, so all conductors have free electrons. That's what makes them conductors. They're not bound to a particular atom, they just sort of float there on top of the surface of the metal. Work needs to be done to remove the electrons from the metal though. Delocalized electrons have continuous range of energies from a minimum to a maximum. So the maximum ones are going to come flying off, the minimum ones are just going to float off of the surface and sit there. The minimum doesn't matter much to us, but the maximum is characteristic to each metal. So we can determine what metal we have by working out what the energy is required to get the electrons off of it. Which is cool. So I could give you a random metal and a range of values, and you could go out and determine what it is using the photoelectric effect. We don't do that, but you could. Okay. So consider the energy levels of copper. All the energies below negative 4.7 electron volts are permissible. So every energy below that is available. But there is a gap between negative 4.7 and 0. So an electron can be here in the blue zone, or it can be up here, not attached to copper, but it can't be in the white area. So it can't have an energy of negative 2.2 or negative 3 or any of those. They don't exist. They're not available levels. So if you had an electron there, what do you think would happen? It's going to go down. Unless you could somehow get energy into it instantly and it would go up, more likely it will go down. What this means is a minimum to get the most energetic electron is sitting right there on that line, the negative 4.7 line, which means you need to put 4.7 electron volts in to get that one to jump up to 0. What happens if you put 10 electron volts into that one? It goes up here somewhere. It has more energy as it comes away. But if you put exactly 4.7, it goes up to here, and it just sort of floats there. Doesn't have any energy to break away, but it's not attached to the copper anymore. Just like, hey, look at me, I've got energy. This value, the negative 4.7 or 4.7, it doesn't matter which way you go with it, is what's called the work function of a metal. It's the work that is required to remove an electron. There are 4 major properties of photoelectric effect then. Do you want a break?